Hello, I'm Takafumi Arakaki. I'm a postdoc in MIT Julia Lab. In this talk, I'd like to present the design ideas behind JuliaFolds. So, parallelism is hard, right? But why? Is it because avoiding races is hard? Maybe avoiding deadlock is hard? Or is synchronization that is hard in general? Or maybe you can deal with all of these, but still worrying about performance like contentions. But these are not parallelism. These are concurrency. And concurrency is hard. It comes up with parallelism and sometimes mixed with parallelism because concurrency is required for describing or controlling how the parallel computation happens. And you have to do it in hardware specific ways because they have different performance characteristics and they have to control in using their specific APIs. And not just that, concurrency is inherently hard. Like, just look at how long it took for C and C++ to get atomics right. It took almost a decade for them to come up with a well-defined weak memory model. Okay, maybe mentioning weak memory model wasn't fair because it's hard, but even good old APIs like locks have problems. Like, how do you control the locking order? It's not composable. And even really nice APIs like channel can be very hard to use unless you stick with common patterns all the time. Well, so this problem happens whenever we try to coordinate how the computation is done. So maybe stop that. That is to say, we need to figure out a way to describe what to compute and not how. Okay, I won't say we should go full SQL, but can we at least specify less? Like more loosely specifying how the computation is done. And I would say it's possible. And a quintessential example of this is the higher order function reduce. If you look at the doctrine of reduce, it has a sentence. The associativity of the reduction is implementation dependent. Maybe a bit cryptic, but actually it's simple. It means that reduce of plus of A and A, B, C can be computed by adding A and B first or adding B and C first. Or to be more specific, reduce implementation is allowed to rely on this freedom of choice. It means that the core of reduce is not specifying how to do the computation. The equation specifying what to compute is oblivious how the parentheses are inserted. It means that for computation, arbitrary grouping of the elements is allowed. Since arbitrary grouping is allowed, the reduced implementation can choose, for example, to compute different groups in different CPUs. So this is why reduce is a very useful parallel API. Okay, but maybe you're wondering if it is actually expressive enough. And of course, I would say yes. And here's why. So stepping back a little bit, let's think about sequential programs. We write for loops in serial programs all the time, right? And this is like the main selling point of Julia. Handwritten loops are fast. In JuliaCon 2019 talk, I presented that for loops and left fold, fold.jl, are actually equivalent. So in a way, for loops is just a syntax sugar of left fold. And by the way, for loops are different from arbitrary loops. You can write with while loop or you can transform some while loops to for loops, but the relationship to left fold is not obvious. So that's what I meant by structural loop. This is for contrasting with while loop, which is unstructured. Okay, so now let's look at the parallel version. We don't have very expressive parallel for loops in Julia in the Julia language yet, but given that how handwritten for loops are super useful, I think we want some ultimate parallel for loop that is super useful. We don't know how it looks like, but we know what the parallel version of left fold is. It is the reduce function. So if we can define a syntax trigger of reduce, and if it looks like a for loop, it should be a good starting point of finding parallel for loop, isn't it? So this idea is implemented in a package called FLoops.jl. So let me skip kind of proving that this adding such syntax trigger is possible. Rather, I'd like to take this relationship as given for now, because it will explain why reduce is apparently super useful, and it will make sense to latch onto them. In fact, JuliaFolds is a group of packages solely based on this idea. So here's my imagination of how to structure parallelism in Julia. The lowest layer has packages that define abstract protocols, and on top of them, there are three categories of mostly orthogonal concept: algorithms, executors, and data structures. Algorithms here means that ways in which the binary operators are composed. The most popular example here is probably online.jl, which is much older than JuliaFolds, but it actually fits nicely into this picture. My package Transducers.jl proper also fits in this package in this category too. Data structures are probably very easy to understand. For example, GPUs have their own memory space, and so it's easy to see why it is essential category. But even on CPU, non-array data structures like dictionaries and strings need to have a different implementation of the protocol. Also, we can fit composite data structures like zip here. Another interesting composite data structure is a lazy implementation of the table.jl operation, or equivalently the sparse dot product. And finally, the executor combine algorithms and data structures together and then deal with the scheduling aspect of the parallel computation. It is important to decouple this from the data structures and algorithms. For example, it is perfectly reasonable to loop over unit range from 1 to, I don't know, million on GPU. If the execution were dispatched on, for example, on data structures, it is impossible to do this kind of operation. On the on the other hand, there's a sensible default in many cases. So if the input is QRA, then you would want to run it on GPU. So ideally, the users don't have to touch it so often. And finally, it would be useful to have a high-level API on top of these three components. For example, Floops provide a for loop syntax trigger for using all these components. And Folds.jl provides a functional API that is mimicking the ones in the Julia base. So maybe it's still kind of abstract. So let's try to build something concrete, like a parallel map. It's actually just a one-liner as shown in this slide. Is the map reuse, blah, 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 vcat and xs. But let me explain why or how it works. So first, we have some element-wise computation, f that maps to x's to y's. Then each element is transformed into what I call singleton solution, like a vector containing just y1. This is the output you want if the input is if the input only contains one element. The computation up until this point can be done in completely parallel. Then we have to combine these singleton solutions. There are various ways to do it. If we do it with left to right single sweep, we have the usual sequential implementation of map. Instead, if we do it pairwise, as in slide, we have the divided and conquer implementation of map. A parallel map with a good performance is somewhere in the middle. But obviously, you might have noticed that this implementation would be very slow, right? So how do we optimize this? Using the dispatch system and um, and implementing performance specialization is always possible. For example, if the input is an array, you can pre-allocate the output, and this can also be done with the reduce. But let us focus on generic solution first for now. So one of the problem here is that the vcat allocates a new array every time it is called. This is bad for performance. But the good news is that arguments to vcats are never used again. So we can optimize it as in-place append. However, append would be problematic if the array in the first argument cannot hold elements in the second array due to some kind of type constraint. Pre-computing required type is impossible to do in Julia, so it would be nice to have a variant of append that can automatically upgrade element types. This is what this double bang append function does. And the package bang has more functions like this. That is to say, a function tries to function tries to reuse the memory in 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 the argument, and if it works, mutate the input and return it. If it does not work, just allocate a new one. This pattern is very common. In fact, this pattern is also famous outside of Julia. For example, scheme programmers call it this linear update, which is a term inspired by linear type system. Since this is a very useful pattern, reduced implementation in JuliaFolds support this explicitly. So going back to the map implementation, another problem is that there are many allocations of singleton solutions, but it is easy to solve. For example, we can use what I call a singleton vector from microcollections.jl. It is just a very lightweight immutable vector that can hold single element. And so the overhead is almost always zero. So we now just derived a very efficient and generic implementation of map. It works well both in single and multi-threaded executions. And the most important thing here is that we only described what to compute and not how. This is why it works both single-threaded and multi-threaded program. Another nice aspect of uh, of this approach is that it can be generalized to other output collections quite easily. In fact, we can use exactly the same pattern for dictionaries and sets, for example. We just need to use different functions for combining them. It's merge for dictionaries and it's union for sets. Okay, but maybe map is too basic, and I'd like to show that reduce-based parallel protocol is much more extensible. For example, we can easily add an API for previewing the real-time state of the reduction. It's implemented in a package called Folds Preview. As you can see, with just 11 lines of code, I can use online stats for reduction and get a real-time preview of real-time feedback as plot. It works with threaded and distributed executors. So here's how it works. In a parallel reduction, each worker thread or worker process has their own local intermediate reduction states, the accumulator. What Folds Preview does is to combine these accumulators and calculate the latest global view of the result, like continuously. And an interesting aspect here is that most of the complex management of the states can be completely automated. This is because the reduction protocol clearly defines how to merge these intermediate accumulators. The only limitation here is that the reduction itself has to be commutative, or at least approximately. Otherwise, it's hard to make sense of the preview result. Another interesting computation I've tried recently was a group by operation on GPU. For this, I've implemented what I call reduce partition by transducers. These are two binary operators involved here. So this transducers first computes intra-partition operation reduction using one of the binary operator, which is this O plus operator, and the result of intra partition reduction is fed to the another binary operator, which is this O plus operators. And using the reduced partition by transducer, we can do all of these reductions in one go. Also, since this only uses basic JuliaFolds protocol, it's executor agnostic. And so that's why it can be executed on GPU or actually in any other execution context. One catch here is that the overall reduction is now non-commutative. So the question is if we can have a non-commutative reduction on GPU and make it fast. So it's easy to naively implement non-commutative reduction on GPU, and actually it is not so bad in many cases when compared to just CPU, but it's actually more than 20 times slower compared to the implementation in CUDA.jl, which fully exploits the commutativity. But it turned out that we can make it even faster with some care to the coreless memory access. For those who know GPU programming, it means that I have to use shuffled or juggling all these accumulators all the time, which introduces some performance overhead. But interestingly, it's only about 10% slowdown compared to the commutative version in CUDA, which is surprisingly good news to me. Of course, a flip side of this story is that commutativity is still essential for optimizing reduction on GPU. And probably should add some commutative executors in JuliaFolds as well. So I can keep going about features I like in JuliaFolds, but we don't have all day. So let me briefly discuss the protocol. So if I if I compress the JuliaFolds protocols, it will look like this. First of all, um, there is this serial iteration protocol, which has start, next, and complete functions. This is a way to inject the code in loop header, loop body, and loop exit part. There's also support for break in a parallel compatible way, but I'm omitting in the slide just to keep it simple. In addition to the serial protocol, there's a parallel reduce protocol for combining the accumulators. And also there's a way to split the iteration space, which is called half. Parallel algorithms define functions start, next, complete, and combine. Um, and you can also use higher level APIs like FLoops and Folds to define these functions, or use predefined functions. Um, of them. And parallel collections first has to be a plain collection, so it needs to either iterate function or left for the implementation. Then, if it implements a function half, it can be used for parallel reduction. Finally, executors put these things together and defines actual scheduling policy. When we define some interface in Julia, there's always a problem in how to specify what it is. Also, checking the correctness is non-trivial. One thing I've started doing for this, and both inside of and outside of JuliaFold, is to clearly note the invariance of the interface. It is sometimes called lows, which is famously used in Haskell type classes. It helps the implementer to understand the protocol. Another nice thing about it is that it's quite easy to turn this into automated test, since you can just run the protocol and then on some samples and then check the invariance of them. For example, here is a part of the documentation of the how interface I just discussed. It says that the code snippet in the middle has to evaluate to true for every input collection. It's nice to express the property of interface in a short code snippet like this, since Julia code is much more precise than English. But what laws are good laws? Lawful interface put us in the right mindset, but it says nothing about what to put in it. In parallel computing, I find it useful to latch onto some ideas from algebra because math guides us. It's kind of a hidden theme in my talk. Obviously, associativity is a fundamental requirement of parallel reduction, but it's not just associativity. For example, when you start combining um, several operators, like in the group example, it is important that we have consistent handling of the identity element. Also, commutativity is important for vectorized reduction. We use this all the time, even on CPU for SIMD, but it's much more important for the GPU because how memory works there. It didn't fit into my talk, but distributivity is also an interesting property. For example, you can use it for calculating linear recurrence in parallel. Exactly the same equation can be used for dealing with nested structures like parentheses embedded in a flat array. A keyword here is semi-direct product, and I posted it on Discord some times ago, so please check it if you're interested in this. It's maybe a little bit of a stretch to put this in algebraic properties, but linear update is also important because we don't want to handle mutation. Uh, we don't want to handle mutation consistently in parallel programs because otherwise it's hard to avoid races. To sum up, today I discussed a way to build a parallel infrastructure for Julia ecosystem. I believe developing the protocols around the algebraic ideas is the key. We need to be more precise about the protocol. Lawful interface would be useful for this, and it's not like we can do formal proof or static analysis right away, but it's already useful for documentation and testing. But perhaps more important question is how to know the design is good. Well, that's obviously a very hard question, but my tentative answer is that by taking composability seriously, or to be more concrete, by extending it to different directions. For example, transducers and monoid combinators are literally the tools for composing algorithms. So trying to implement some complex ones has been very good exercise for me, meaning that it helps me finding some improvable points in the protocol. Of course, some more data structures is also important. Adding more data structures is also important since it involves in a reduction in two ways, as an input and also as an output. Supporting multiple executors is also important since the parallelism is essentially the property of the physical hardware. This goes hand in hand with the data structure since GPU and distributed systems have different ways to handling memory. Um, anyway, this is my ongoing attempt to bring composable parallelism in Julia. and I hope you enjoyed it. And thanks for your attention.